today we are going to discuss basic concepts and classifying differential equation. The definition of differential equation. It is an equation containing the derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables is said to be a differential equation, or in short, DE. So these are the following are the differential equations involving the unknown function y. So we have dy over dx equals 5x plus 3. So we have another one, e raised to y times d squared y over dx squared plus 2 times the square of dy over dx equals 1, and so on. So these are now the examples of differential equations involving a known function y. A differential equation is an ordinary differential equation if the unknown function depends on only one independent variable. If the unknown function depends on two or more independent variables, then that differential equation is a partial differential equations. So that's a difference between the two types of differential equations, which are ordinary differential equation and partial differential equation. So classification by order. So the order of a differential equations, either ODE or PDE, which means ordinary differential equation and partial differential equation, is the order of the highest derivative in the equation. For example, we have the d squared y over dx squared plus 5 times the quantity of dy over dx raised to the power of 3 minus 4y equals e raised to x. So by looking at this part, we have d squared y over dx squared. It is said to be that this notation is a second order. So it is a second order, while the other one here inside the parentheses, which is dy over dx, that is only the first order. Do not be mistaken with regards to this quantity being raised to the power of 3. It is just the exponent or raising to the power of 3 of this, the first order. But it is not the third derivative. Otherwise, the third derivative can be written as d cubed y over dx cubed. So that's the difference between the order and just raising it to the power. Now, since the highest order comparing the two terms, the highest power now is 2, therefore it is a second order. So it is stated here that it is a second order ordinary differential equation. Going back to our previous example, so the first example here of dy over dx equals 5x plus 3. So it is now a first order differential equation. The second one, we have e raised to y of d squared y over dx squared plus 2 times the square of dy over dx equals 1. So because of this first element, we have d squared of y over dx squared. Therefore, this is a second order ordinary differential equation. While the third one, looking at the powers of their derivatives, so we have d cubed y over dx cubed, while the other term we have d squared y over dx squared. Then the highest order here, the highest power, is the third power. That is why this is known as the third order of ordinary differential equation. Now, on the next example, we have here the quantity of d squared y over dx squared to the power of 3 plus 3y times the quantity of dy over dx to the power of 7 plus y cubed times dy over dx to the power of 2 is equal to 5x. So in this case, class, to determine the order of ordinary differential equation, do not look at the exponent as a derivative. So where what I'm trying to say is that you focus first here on the d squared y over dx squared compared to dy over dx, not on the power of 7. So these are just the 3, 7, and 2. They are just the powers of this derivative. But the first term is a second order derivative. The second term is the first order derivative as well as on the third term. So comparing the three terms, so this one that has d squared y over dx squared is what we call as the second order of ordinary differential equation. And on the last example, if you encounter this kind of symbol, that's what we call as partial derivative. So therefore, this is partial differential equation. Now, what is the order of this? So looking at this, so the square of the partial derivative of y over the partial derivative of t squared minus 4 times we have partial derivative squared of y over the square of the partial derivative is equal to 0. So looking at this, they are the same second order, okay, with having different more than one variable. So then this is now the second order of partial order derivative. Okay. Now let us put this one into example. We are going to determine the order, a known function, and the independent variable in each of the following differential equation. So for letter A, we have y to the so y triple prime minus 5xy prime equals e raised to x plus 1. So first, we are going to determine the order. So since the highest power there is 3, then for letter A, because of the third power, the 3 primes there, so therefore we could say for letter A, so determine the order. So the order now is a third order. So I will write here third order because the highest order derivative is the third or 3. Then the next question is unknown function. So what is now the unknown function in the equation of y triple prime minus 5xy prime equals e raised to x plus 1. So in that case, class, the unknown function is y. Okay, so I will write here unknown function is y, and then the independent variable there is the variable x. So we have here, and the independent variable is x. So the independent variable is x. Okay, that is now for letter A. Now for letter B, we have t y double dot plus t squared y dot minus sine t times square root of y is equal to t squared minus t plus 1. So the order there is second order. It's because of the y double dot. So I will write here that this is for letter B. We have second order. And then our unknown function is, so the unknown function there is y. So the unknown function is y, and the independent variable is t. Again, for the first line is for the order. So the second line here is for the unknown function, and the independent variable is t. Now for letter C, we have s squared times d squared t over ds squared plus st times dt over ds is equal to s. So the order is also a second order, and then the unknown function is t. Okay, the unknown function is t, and the independent variable is s. Usually, class, the if the equation is given in terms of letter C, usually the independent variable is at the denominator. And for letter B, the independent variable there is in terms of t, which t times 4 means for the time. T means time. Okay, usually this notation is also is being used in physics, but seldom used in differential calculus as well as on the integral calculus. Now for letter D, so I will not write there anymore, but I will just say it. Then we have the order is we have d raised to 4 of b over dp raised to 4 because of this compared to the second term, then the order of this is the fourth order. And the unknown function is b. Okay? And the independent variable is in terms of p. So you just practice this one. So this is now similar to the first four examples a while ago. A solution of a differential equation in the unknown function y and the independent variable x on the interval I is a function of y of x that satisfies the differential equation identically for all x in I. So first question is, we are asked to determine whether y of x equals 2e raised to the power of negative x plus xe raised to the power of negative x is a solution of y double prime plus 2y prime plus y is equal to 0. So how are we going to do that? So first, we are going to take the derivative of this term. On the first equation here, we are going to take the first derivative. Since we have here double prime, meaning to say we have to take also the second derivative. So differentiating now this given of y of x is equal to 2e raised to negative x plus xe to the power of negative x. So taking the first derivative of that, so y prime of x, so we is equal to 2e raised to negative x, and the derivative of e raised to negative x is negative 1 plus, so this is a product rule, we have x times the derivative of e raised to negative x is we have negative e to the power of negative x plus e raised to the power of negative x times the derivative of x is equal to 1. So simplifying this, we have now 2e raised to negative x times 1 is negative 2e raised to the negative x plus multiply this one, this become now negative xe to the power of negative x plus e raised to the power of negative x. Now simplifying this one, so that I can write now negative 2e raised to negative x, positive times negative is negative x e raised to negative x plus e raised to negative x. So we have similar terms, this one, the first term and the last term. So negative 2e raised to the power of negative x plus e raised to negative x. So we have now the answer of negative uh, e raised to negative x minus x e raised to the power of negative x. So this is now our first derivative. So the first derivative now, we are not going to take the common factor of negative 1. So just let it be the answer of the first derivative, that is negative e raised to the power of negative x minus x e to the power of negative x. So this is our first derivative. Now taking now the second derivative of this. So we have the second derivative based on the first derivative, we have negative e raised to negative x, and the derivative of the exponent, which is the negative x, is negative 1 minus, apply product rule here. We have x, so I will just write here a bracket so that we cannot forget the sign. So therefore, we have x times the derivative of e raised to negative x. We can write directly as negative e raised to negative x plus the second term, we have e raised to negative x times the derivative of x is 1. So let us simplify. So we have negative e raised to negative x times negative 1 is positive. So therefore we have now e raised to negative x minus, combine this first, we have negative x e raised to negative x plus e raised to the power of negative x times 1 is e raised to negative x. Now, this using distributive property on the second term to remove the symbol of grouping. So therefore, we can write now e raised to negative x. Negative times negative is positive. So we have x e to the power of negative x, and negative times positive, we have negative e raised to negative x. And simplifying, so there are this one additive inverse, so that will be now cancelled. So the remaining answer now we have x e to the power of negative x. So this will be our y double prime, or the second derivative of the given. Now after that, we are going to substitute that one to our equation, to the solution of y double prime plus 2y prime plus y is equal to 0. Now, if after substituting the value of y prime and y double prime, when it will give the answer of 0 that will be equal to the right hand side, then we could say that this equation is a solution of this partial differential equation. Okay, so let us substitute it now. So we have here y double prime plus 2y prime plus y is equal to 0. So y double prime means x e raised to negative x plus 2 times y prime, which is negative e raised to negative x minus x e to the power of negative x plus y is equal to 0. Now we're going to simplify this one. So we are going to copy the first term and simplify the second term. So we have x e to the power of negative x. Then multiplying this one becomes negative 2 e to the power of negative x, and 2 times the negative xe, we have negative 2xe to the power of negative x, then plus the value of y, which is the original given. So instead of writing y, I will use now the original given, which is now equivalent to 2e raised to negative x plus xe to the power of negative x. So it must be equal to 0, or else it will not be a solution. Now let's try to combining like terms. So combining like terms, we have xe to the power of negative x. So this one and this one are similar terms, as well as this. So we have xe to the power of negative x, and another xe to the power of negative is that the sum is 2xe to the power of negative x minus 2xe to the power of negative x, then that is now 0. So therefore this can be cancelled, that one, and in terms of e, we have negative 2e raised to the power of negative x plus 2e raised to the power of negative x. So they are additive inverse. So therefore, the left-hand side now is equal to the right-hand side. So maybe on the equation above, I can write first a question mark on top of the question of the equal sign, because we are still trying to prove that this equation will be equal to 0. Now, since they are now equal to 0, the left hand side and the right hand side are equal, then we could say that the given equation of y of x is equal to 2e raised to negative x plus x e to the power of negative x is a solution of the given equation of y double prime plus 2y prime plus y is equal to 0. So this is what we call as the ordinary differential equation. So therefore, it is a solution. Or in short, I will just write their solution. So another example, we have is y of x is equivalent to 1, a solution of y double prime plus 2y prime plus y equals x. So first of all, we are going to take the derivative of the given equation of y of x is equivalent to 1. So we have y of x is equivalent to 1. And so taking the derivative of this, so since I have double prime and the 1 prime, so therefore I will take the first derivative and the second derivative. So the first derivative of y of x equals 1 is 0, as well as y double prime of x is also 0. Now, after that, we are going to substitute it here. So we have we are going to substitute the value now of y double prime and y prime. So I will not write anymore the equation. So it's there. So it's our guide. So y double prime is 0 plus 2 times y prime is also 0 plus the value of y, which is the given, we have equals 1 is equal to x. So simplifying this one, 0 plus 2 times 0 is 0. So we have 1 is not equal to x. Since our solution here does not coincide or does not give us exact value on the right hand side, therefore we could say that y of x equivalent to 1 is not a solution. Okay, so that is now the difference between how to tell whether the given equation is a solution of the given differential equation. So even comparing to the previous one, so we after we substitute the value of y prime and double prime to the given differential equation, it is gives us the left hand side equal to the right hand side, so that is now a solution. While here the left hand side now of the after we substitute the value of y prime and double prime, it is not equal to the right hand side. So simply we could say that it is not a solution. So we have another problem. We have to show that y is equal to ln of x is a solution of xy double prime plus y prime is equal to 0 on the interval of 0 to positive infinity, but is not a solution on interval that is equal to negative infinity to positive infinity. So let us start here on the interval of from 0 to positive infinity. So let us take first the derivative of the given equation. So we have y is equal to ln of x. Now we're going to take the derivative of that. So we have y prime is equal to 1 over x times the derivative of x times 1. Therefore, the derivative of that is just still the same as 1 over x. And for y double prime, so the expression of y prime is equal to 1 over x, or is that is equal to x to the power of negative 1. So taking the derivative of this, so negative 1 x to the power of negative 2, or simply write negative 1 over x squared, and that is now the second derivative. So this one is the first derivative, or you may use also the other form of x to the power of negative 1. Now after that, we are going to substitute the value of y prime and y double prime into this differential equation. We have x y double prime plus y prime is equal to 0. So we have x times the meaning of y double prime is negative 1 over x squared plus y prime, which is 1 over x, is equal to 0. So simplifying this, so we have x times negative 1 over x squared, or you may use cancellation. So this 1x here is cancelled and the 1x here is cancelled. So therefore, the product now we have negative 1 over x plus the second term of 1 over x is equal to 0. We know that the first term and the last term, they are additive inverse. So therefore, the left-hand side now will give us equal to 0. So the left-hand side and the right-hand side now are equal. Therefore, we could say that the given equation of y, therefore, y is equal to ln of x is a solution. Okay, take note that it's only a solution on the interval of 0 to positive infinity. So note that y equals ln of x could not be a solution on the interval of negative infinity to positive infinity, because the logarithm is undefined for negative numbers. Again, so on the first condition, on the interval of from 0 to pi, we could say that the given equation of y equals ln of x is a solution because it gives us equal, the left hand side and the right hand side are equal. That is why we are saying that y equals ln of x is a solution on the interval of 0 to pi. But on the second condition, we could say that y is equal to ln of x could not be a solution on negative infinity to positive infinity, since the logarithm is undefined for negative numbers and 0. So again, since the logarithm is undefined for negative numbers and 0. Show that y is equal to 1 over x squared minus 1 is a solution of y prime plus 2xy squared is equal to 0 on the interval from negative 1 to 1, but not on any larger interval containing I. So first, we're going to take the derivative of the given equation. So we have now y is equal to 1 over x squared minus 1. So taking the first derivative, so I will just rewrite this one. That expression is equivalent to x squared minus 1 to the power of negative 1. So I'm just rewriting the given into this form so that it will be easier to take the derivative. So we have now y prime is equal to negative 1 times x squared minus 1, so to the power of negative 2, times the derivative now of x squared minus 1 is just 2x. So therefore, we are getting 1 times 2x is negative 2x over x squared minus 1 to the power of 2. So we have here the first derivative. Now taking a look on this equation, we have y prime plus 2xy squared is equal to 0. So meaning to say, we need only to take the first derivative. Now we are going to substitute our value of y prime and y from this equation. So we have y prime plus 2xy squared is equal to 0. So the meaning of y prime is negative 2x over x squared minus 1 to the power of 2 plus 2x times the value of y, which is the original given. We have 1 over x squared minus 1, and this is now raised to the power of 2. Okay, so simplifying this, we can write now. Uh, I will copy only the first term. We have negative 2x all over x squared minus 1, so quantity to that, the power of 2 plus, okay, so by using distributive property, so we can write here 2x because times 1 squared is just equal to 1. So 2x times 1 is still 2x. Now on this denominator, so I will just write here the square of x squared minus 1. So x squared minus 1 and then raised to the power of 2. Or I will say the square of x squared minus 1. So I forgot to write 0 on the right hand side. So let us check. So the given now on the first term and on the second term, they are they are of additive inverse. Okay, because we have the same denominator, the square of x squared minus 1, and the numerator now is negative 2x plus 2x, so they are additive inverse, so therefore this is now the left hand side now is equal to the right hand side, which is equal to 0. Therefore, we could say that y equals 1 over x squared minus 1 is a solution because of that statement that the left hand side is equal to the right hand side, which is equal to 0. Okay, now however, the second condition, it says that but not on any larger interval containing I. We have to take note that however, that 1 over x squared minus 1 is not defined at x equals plus and minus 1. Okay, or else the denominator becomes 0, because if x is 1, so 1 squared is 1 minus 1, it's 0. So 1 divided by 0 is undefined. Okay, or we can use another one. So I am trying to solve for x. In that case, that's I was trying to solve for x squared minus 1 is equal to 0 and solve for x. So we have x squared is equal to 1. Then x now will give you the value of positive and negative 1. The square root of 1 is plus and minus 1. So in that case, class, the given equation of 1 over x squared minus 1 is not defined at x equals plus and minus 1, and therefore could not be a solution on any interval containing either of these 2 points. Okay?